Well, hi everybody, Mike. It's a pleasure. It's really a pleasure for me to take part in this special session. As was said, the talk will be relating ASR lab test to outdoor exposure site. So we have heard from Karen that ASR is indeed a chemical reaction between reactive aggregate particles and the pore solution of the concrete that results in the formation of a secondary alkali-silica gel that will create pressure, expansion, and cracking of the affected element. Although this phenomenon or this pathology has been found in many countries around the world, it's generally only a few cases of structures have been demolished essentially because of ASR, but we know that from experience that ASR is a pathology that affects significantly the durability, the serviceability, and the safety of concrete structure all around the world. So it's really important for engineers and practitioners to actually prevent ASR in new concrete structure and new concrete construction. How do we do that? We do that by, if we can, using non-reactive aggregate, and we know that it's in some regions it's not possible to do that. We can limit the alkali content in the concrete mixtures, and this we know amongst a number of parameters that can vary according to one aggregate to another. So the threshold value of alkalis in the concrete that will generate deleterious expansion will vary from one aggregate to another. And we can also use it, we can also prevent ASR by using sufficient amount of effective supplementary cementing materials and chemical admixtures such as lithium-based admixtures. Back in the 80s, Chris Rogers from the Ontario Ministry of Transportation formed a committee to develop rapid and reliable test methods to prevent ASR. And at that time, Mike and I, we were young participants, and in that committee that was very active, and we were also very active in this committee. That resulted in indeed the establishment of new test methods, also establishment of reliable supplies of known reference reactive aggregates that have been used in many countries around the world. Everybody knows about the famous Spratt limestone from Ottawa that has been used in very large number of studies all around the world. And those committee meetings were actually located in different parts of Canada. We had field trips across the country, and it was more also stories about friendship and hard work in this committee. So it was a real good time. In the early 2000s, the CSA Committee on ASR actually introduced two new standard practices that were later actually adopted or resulted in new methods and new practices in different countries around the world, including USA, Australia, Europe, and Jason is going to talk a bit more about that in the next presentation. But basically, in the first standard practice, the first step of this practice is the determination of the reactivity of concrete aggregates. So it's a step-by-step approach that will actually allow us to evaluate the potential reactivity of aggregates using different test methods, as you can see here. And then based on the establishment of the aggregate reactivity class, this information is used in the analysis of the size and the environment to which a concrete structure to be built is exposed to determine a level of risk of ASR. That level of risk of ASR is compared to the type of structure to be constructed, the type of structure, the criticality of the structure in order to develop prevention level. And those prevention levels, which varies from mild to exceptional, actually will result in recommendation regarding the limitation of alkalis in the concrete, and also to recommendations on the amount of supplementary cementing materials to be used. So this table here is providing recommendations in this prescriptive approach for fly ash, slag, and silica fume replacement of an high alkali cement in order to prevent ASR. And all those numbers in the table were actually generated over the past decades through field work, lab work, and so on. So those numbers have been established based on knowledge that we had at the time of development of this standard practice. The second standard practice is actually a performance approach where the accelerated motor bar test and the concrete prism test are used in order to generate some lab specimens where the high alkali cement would be replaced by different proportions of supplementary cementing materials, and the local reactive aggregate can be used in order to establish how much of the SCM you can use in order to prevent the expansion under a certain acceptance limit for the structure to build. Obviously, those tests that we use in the lab last from 14 days to 2 years. They're quick tests, and their reliability is actually limited to the fact that they actually use different accelerated processes in order to generate quick and hopefully reliable results. But basically what we need to do is to make sure that those test methods that we use in the lab actually correlate well with what is seen and what is observed in the field. So there are not too many cases where we have data and information about the field performance of preventive measures against ASR. And one of those is this great paper by Mike and colleagues, where there have been revision of a number of cases around the world where fly ash and other preventive measures have been used in the construction of large structures, such as this hydraulic dam in the northern part of Ontario in Canada, the Lower Notch Dam. We had the chance, actually, the team, Mike, Doug Hooton, Chris Rogers, and myself, to visit that dam after 25 years and 40 years of service. And then we took cores and examined those cores in the lab by petrographic examination. And this here graph shows a damage rating index, which is an indication of the damage in the concrete. The higher values represent high damage condition in the concrete, lots of cracking in the aggregate particle in the cement paste. And as you can see here, after 25 years in service, the lower notch concrete has a very, very low damage rating index. After 40 years, similar values of damage rating index, no cracking in the aggregate particle or the cement paste. So this information is extremely useful to practitioners and researchers who work in trying to establish recommendations for ASR prevention. But in most cases, in recent years and for the past 2 or 3 decades, researchers have been using outdoor exposure sites for evaluating the effectiveness of preventive measures against ASR. And the work of the Building Research Establishment, BRE in the UK, by Mike and the team there was very, very important. They have established a number of exposure sites back in the late 1980s, where they evaluated concrete mixtures with different reactive aggregates, dosages of high alkali cement, fly ash, slag, metakaolin, lithium-based admixtures. And from those studies, basically the main conclusions was that the use of fly ash actually was very efficient in reducing expansion and cracking in the field specimens. There appeared to be no contribution of alkalis by the fly ash selected at the dosage tested, which were 25 and 40%, up to 40% of the high alkali cement. And the fly ash at that time had an alkali content of about 3.5 to 4%. And also they found that a reasonable prediction of the amount of fly ash to prevent expansion with flint aggregates can be obtained from the 14-day accelerated mortar bar test, which is good news because, for practitioners, waiting 2 years to get results in the lab is sometimes not possible. For having a test with 14-day results that can be reliable, it's extremely interesting. So we have done a lot of compilation of data, and this paper by Mike and colleagues back in the mid 2000s, data were compiled from testing that was carried out in 3 labs, and as we can see, for close to 200 mixes, we could see that actually both tests, the concrete prism test after 2 years and the accelerated mortar bar test after 14 days, were actually giving similar results in about 80% of the cases. But in those 2 cases, comparing the accelerated mortar bar test to the concrete prism test is comparing the results of 2 accelerated tests, which both of them have limitations. So basically, we need to continue the work in comparing the reliability of those tests against long-term exposure blocks in the exposure sites. And that work showed that from a number of concrete mixtures, a disconnect existed between the results of laboratory and field testing, because significantly greater level of alkalis were required to actually generate expansion in the lab. And we found out that over the years, that leaching of alkalis from the test prisms in the concrete prism test was the main source of that disconnect that we could see between the lab and the field testing. This has been highlighted through a number of cases. In the case of the outdoor exposure site in Kingston, Ontario, set up by Chris Rogers and his team, they have used a reactive aggregate from the Spratt Quarry in Ottawa. They have made some blocks and slabs that they monitored for many, many years with control mixtures, binary and ternary mixtures. And what they found is that with time, there was continuing expansion of some of those mixes. And it was interesting to learn also that with the low alkali cement, with time, there was increasing expansion and cracking that was actually not necessarily picked up in the lab testing. As you can see here, for the 2-year concrete prism expansion, the low alkali cement had a limited expansion in the concrete prism test, such as also the 20% fly ash mix or the 25% slag mix. So the 2-year concrete prism expansion was just on the limit that is used in the test procedure compared to the exposure site blocks that expanded much more in the field. Another exposure site was set up in Ontario at the Picton cement plant. As you can see here, different mixtures were implemented in large slabs, and also field lab specimens were made to compare the results from the field and the lab. We had a chance to look at some cores that were extracted about 18 years in service. And as you can see here, for the control concrete, a lot of cracking in the aggregate particle and the cement paste that resulted in very high damage rating index. Same thing was observed with the 8% silica fume and 35% slag mix, where we found some signs of ASR in the aggregate particle and the cement paste, while the ternary system here were still pristine after about 20 years in service. And if we compare the results to the 2-year concrete prism test, we can see that the reactivity that we can see in the field can hardly be picked up by the concrete prism test after 2 years of expansion monitoring. We found some similar results also from the CanNet study in Ottawa. Again, large team there, worked together with Mike and the team from Texas, now also Jason in Oregon State. We made a large number of blocks that were monitored for over 25 years. And one graph from that study is showing actually the expansion in the lab as a function of the expansion after 15 years from blocks in the field. As you can see, again, some disconnect between the lab results and the field, with higher expansion in the field that we found over the years. So all that data actually of that disconnect between lab and field is increasing the requirement to continue the research. And a new project under the NCHRP was launched about a couple of years ago, and the team is working very hard trying to improve the test methods that we have right now. And this is basically what Jason is going to talk about in his presentation. So amongst my contribution, I have learned a lot with working, and it's always a pleasure to work with Mike. And we learned a lot about the critical importance of validating the accelerated laboratory test results against the field performance. This is extremely critical because what we do in the lab is meant to accelerate a process that takes a lot of time in the field. And we all know, working in durability of concrete, that we have to take most of the time with a grain of salt what we get in the lab. And the requirement to compare that to field performance is extremely, extremely critical. And the exposure site work is actually providing unique database to provide better recommendations for practitioners, but also for future modeling efforts. A lot of people in the young generation actually will have the chance to access lots of data from long-term field exposure sites that will be useful for evaluating and correlating lab and field information. And also all that information is interesting in providing a better understanding of the prevention mechanisms involved with the use of supplementary cementing materials and other preventive measures. So, Mike, thanks a lot for all your immense contribution. It's been and it's still a big pleasure for me to work with you and all the friendship through this collaboration.